Hello, my name is Sandra Cruz-Pol, and I'll be talking about why picking the wrong frequencies can cause and harm you and your research. This is an introduction to the radio frequency regulations. This is an outline of what will be covered in this webinar. After a brief background and motivation, I'll present an introduction to the radio regulations at the national and international levels, then talk about some factors to consider when selecting a frequency of operation, introduce NSF's two spectrum managers, and next I'll go through some basic concepts and acronyms used in the RF spectrum world. So let's start. All of us use radio frequency waves every day, numerous times throughout the day for our personal activities like texting and checking the weather, using GPS, using a Bluetooth mouse, or even watching this webinar through Wi-Fi. In fact, if our eyes were able to see all the RF signals around us, we probably wouldn't be able to see past a few meters ahead of us. It'd be swamped with frequencies from TV stations and a whole bunch of other applications. What most people don't know is that quite often, industries, radio stations, and even civilians pay thousands of dollars in penalty fees due to their lack of awareness about the RF spectrum regulations. Such is this example from 2018, where a cell phone company had to pay over $600 million to the FCC for violating radio regulation rules. This presentation is an introduction to the radio frequency spectrum regulations and could potentially save you a lot of money and research time. Did you know that it is illegal to design a device to transmit at certain frequencies? In fact, in some instances, there have been devices successfully designed to perform specific tasks for transmitted at a certain frequency. But when they request a license to operate, they find out that it is illegal to transmit at that frequency in that country. You might even need an experimental license for research that involves transmitting at some frequencies. And did you know that the United Nations has a body to regulate RF signals used all over the world? In fact, even your Wi-Fi modem could cause RF interference. This is one such an example, from Wi-Fi routers to an airport weather radar. As you can imagine, this poses a hazard to society. Because it could prevent the detection of a storm. And we could go on and on, showing numerous examples of penalties, fines received for violating the radio regulations in many ways, such as transmitting without a license, transmitting at a frequency outside the assigned bandwidth, or transmitted at a power level higher than the stipulated on the radio regulations. These fines can be anywhere from a few $1,000s to millions of dollars. The first things we need to understand is that the radio spectrum is a limited resource, yet increasing applications and devices rely on it for operation. Therefore, radio regulations are constantly changing in a process led by an international United Nations agency. An example of a change in radio regulations are biomedical devices, which historically used to operate at frequency corresponding to the TV channels 7 through 13 and 14 to 46, and also between 450 and 470 megahertz on a licensed but secondary basis. But due to frequent interference, which impaired the performance of these devices, in 2002, the radio regulations were updated to designate new bands for the Wireless Medical Telemetry Service, or WMTS. Specifically, 608 to 614 MHz, 1395 to 1400 MHz, and 1427 to 1432 MHz. Operating in these frequency bands should decrease the chance of interference from the television broadcasters and private land mobile licenses. So the objectives of this webinar are to learn basic concepts of radio frequency spectrum management, including agencies that regulate their use, And second, learn basic radio regulation processes and how you can select the appropriate frequency. Moving on, let's see why we need radio regulations. When we realize all the different types of technologies that rely on the radio waves, it is very hard to imagine a world without them being available. No hurricane monitoring, no postal package tracking, no weather forecasting, no GPS, no solar storm protection, no cell phones, texts, calls, mobile phone applications, Wi-Fi internet, FM radio, just to mention a few. All of these are only possible thanks to sharing the radio frequency signals with minimum radio frequency interference, or RFI. Numerous scientific and engineering applications also use this radio spectrum, including El Niño event monitoring for helping forecast extreme weather all over the world, rain and wind remote sensing for renewable energy management and weather forecasting, cybersecurity for extra bandwidth needed to encrypt the information, and solar storm forecast to prevent GPS satellite and energy grid disruptions. Soil moisture monitoring is also used for agriculture and fire-prone areas mapping, just to mention a few. Through all the previous applications, we have seen that engineers and scientists can design and build amazing instruments that use radio waves to help society in so many ways. But it doesn't matter how good and expensive these instruments and devices are if RF deems our sensors unusual. That's why RF spectrum management is so important, which is a process to ensure that all the users of the radio spectrum can share it efficiently for the benefit of society. This here is a section from the US Table of Frequency Allocations. Each color represents a different use called service. Each country has its own frequency allocation table, which might be a bit different from each other. The tables summarize how the spectrum is used and shared among numerous users, given that the spectrum is a limited resource. I will tell you a little bit more about that later during this webinar. Since the radio regulations are not the same all over the world, this poses an additional challenge for RF spectrum managers, which is that nowadays the global markers make it so easy to order anything online, even if it's a device that is illegal in the United States. Such is the case for the GPS and cell phone jammers, which are both illegal and potentially dangerous because they can block signals from airport weather radars needed for safe plane navigation. The radio frequency spectrum is conventionally defined as the part of the electromagnetic spectrum encompassing frequencies from 3 kHz up to 3,000 GHz, according to the ITU radio regulations, Article 2, Section 1 of 2016. However, several uses extended to frequencies approaching the edge of the infrared part of the spectrum into the higher terahertz. We humans can only see the visible part of the spectrum, yet we can perceive IR waves in the form of heat. Most television sets use IR receivers so that they can be switched with a remote control unit. Night cameras use IR to detect humans because we, humans, emit this frequency more than any other one due to our body temperature as given by Planck's law. However, the infrared part of the spectrum is not part of the RF. The RF part of the spectrum includes microwave, millimeter wave signals such as AM, FM, and higher frequencies. Now, as I said, the radio regulation process is led by an international body. The United Nations has a specialized agency for this, the ITU, or International Telecommunications Union. This is particularly important for coordinating licenses for satellites, since satellites circulate all over the Earth, crossing international boundaries. For managing the global radio spectrum, the ITU divides the world into 3 regions. The Americas are in Region 2. Because applications and uses of the radio spectrum change rapidly, There's a need to revise the radio regulations regularly. So the ITU coordinates the WORC, or World Radio Communication Conference. It is held every 3 to 4 years, typically in Geneva, Switzerland, and typically lasts 4 weeks. The radio regulations have international treaty status, whereas the ITU recommendations are non-mandatory unless they are incorporated by reference into the radio regulations, but are generally followed out of convenience. This is an example of one of the ITU recommendations for satellite antennas, RTUR-S 672. S stands for satellite. Sometimes the radio regulations have exceptions for specific regions, and this is when the national level comes into play. The United States is a special case from most countries since it has 2 agencies that regulate the spectrum. The Federal Communications Commission, or FCC, is for all non-federal users, and the NTIA, or National Telecommunications and Information Administration, is for federal users. The structure of the US process to prepare for the World Conference replicates the international committees and working groups, both within the FCC and the NTIA. As part of the US process to change the radio regulations, the FCC has what is known as the Notice on Comment rulemaking. In this process, the FCC gives the public a notice that it is considering adopting or modifying spectrum rules and seeks the public's feedback in order to hear comments from the community. This is done by publishing the NPRM, or Notice of Proposed Rulemaking. The process actually starts with an NOI, or Notice on Inquiry, to seek information in order to better prepare the NPRM. An NPRM may be followed by a further Notice of Proposed Rulemaking, or FNPRM, if the comments led the agency, FCC, to make considerable changes to its original proposal. Any interested party may comment. The FCC typically gives 60 days for public comment and an additional 30 days for reply comments. The final new rules are issued in what is called Report and Order. NTIA manages all the spectrum assigned to the government. This is done with the advice from the IRAC, the Interdepartment Radio Advisory Committee, which is composed of representatives from the various federal agencies that use the spectrum extensively. The NTIA shares the IRAC. Now, let's take a closer look at the section of the U.S. Frequency Allocation Table. For each frequency range on the table, there are different colors. Each color represents a service, which is synonym here of application or use. When there's more than one color, it means that several services are sharing that frequency range. If the service is written in capital letters, it means that it is a primary service. If it's in lowercase, it's a secondary service. And this is in relation to the priority to use the band and to be protected from it, as we'll see later. Now, for more detail, the NTIA publishes the table in this format, showing each particular frequency range. This is an example from the NTIA Manual of Regulation for the Spectrum. It's also known as the Red Book. Notice that they list the international allocations on the left column and the US federal and non-federal allocations on the right column. And again, here they use the uppercase and lowercase to designate primary and secondary services respectively. And also note those numbers. Those are called footnotes. Footnotes contain very important information such as regional or geographical exceptions, power levels, and more. The international footnote starts with the number 5. When they appear in the US tables, it means that they have either been accepted by the FCC and or NTIA. The footnotes that start with US refer to federal and non-federal government allocations. The ones that start with NG are for non-federal government allocations, and finally the ones with G apply only to federal government allocations. This is an example of an international footnote for ham radio or radio amateur. Here's another example for the ISN, or Industrial Scientific Medical band. And this is one example of the US footnote for radio astronomy service. So you can see footnotes contain a lot of detailed information about how to share the spectrum. So how do we choose a frequency? It depends. Some scientific applications can only select the frequencies where certain physical phenomena occurs and can be observed. For instance, this graph shows the chemical resonance for several important molecules such as water vapor, oxygen, and others that need to be sampled in order to feed meteorological models and other models. This other graph helps engineers and scientists select the frequency most sensitive to desirable parameters such as sea surface salinity or wind speed. Other applications choose the operating frequency in order to minimize the cost of the equipment or the atmospheric propagation attenuation. In general, lower frequencies experience less atmospheric attenuation, and higher frequencies allow for smaller components, such as antenna size, for a given gain. So the spectrum managers take all of this information into account when considering changes to their radio regulations. There are spectrum managers at all kinds of companies, such as Boeing, Google, Nokia, and at government agencies such as NOAA, FAA, NASA, among many others. They are in charge of managing the spectrum, attending spectrum meetings at national and or international levels, working with frequency assignments or licenses, and protecting the access to the radio frequency spectrum for their particular users. At the NSF, we have two people designated as the NSF spectrum managers, Dr. Ashley Soderer and Jonathan Williams, who will be available during the Q&A session of this webinar to answer any questions you might have about their role. And also, here's their contact information. And lastly, I'd like to cover some common concepts used in radio frequency spectrum management. To illustrate the difference between allocations and assignment, let's look at the zoning map in a city. As shown in this map, there are areas in the city that are used for business, that's the commercial zone. There is also an industrial zone, as well as a residential zone and recreational areas. Just because a zone is residential doesn't mean that you can build your house there. You need a permit. In the same way, a frequency band might be allocated for mobile aeronautical telemetry, but you will still need to apply for an assignment or a license in order to be able to transmit at that frequency. There are two allocation types. Primary allocation grants specific services priority, as defined in this paragraph. Secondary allocations involve services that must protect all primary allocations in a particular band, and they must not cause harmful interference to and must accept interference from primary users. The FCC establishes which frequencies devices could transmit without having to apply for a license. That's how UNI was defined as the unlicensed national information infrastructure. Each country defines their level of allowable transmit power, bandwidth, whether they can be used indoor or outdoor, and different available frequency channels. They all have access to the same frequencies without protection. This is probably why sometimes my Bluetooth mouse stops responding when someone is using the microwave oven. They both use frequencies within the 2.4 gigahertz. In the United States, the unit bands are defined as seen on this table. The table shows the frequency ranges for each band. It is important to note that Unit 2B and Unit 4 are not unlicensed. They do require licenses. Also, it's good to note that in spite that some unit devices can be said to work outside the frequency band, please don't, because you could be transmitted at an illegal frequency. Another example of unlicensed use are microwave ovens, which operate at 2.4 gigahertz. Despite heavy shielding, the oven's high power emissions could sometimes interfere with neighboring frequencies. So it was decided that they should be given a few megahertz in both directions. These are called guard bands. The ISM band was originally at around 2.54 gigahertz, but later expanded to frequencies as low as 6.7 megahertz, all the way up to 245 gigahertz. Examples of unit devices that use ISM bands are cancer treatment, cordless phones, IoT devices, Bluetooth devices, walkie-talkies, RFID, and Wi-Fi. Cell phones use some ISM bands too. Another important parameter is the specific absorption ratio, or SAR. It's a measure of the rate at which energy is absorbed by the human body when exposed to radio frequency, or an electromagnetic field. It is defined as the power absorbed per mass of tissue and has units of watts per kilogram. The SAR levels vary for different parts of the world. In the US, a certification is required by the FCC for all transmitters. Another important definition is the sensor type. Active sensors such as radar have a transmitter that sends an electromagnetic signal up, illuminates a target, and a receiver that measures what bounces back from the target. Passive sensors don't have a transmitter, only a receiver. In fact, a radiometer is a very sensitive receiver that measures thermal electromagnetic emissions or noise power from natural media. The design of a radiometer allows measurements of signals smaller than the noise introduced by the system itself. That's what makes them so vulnerable to RFI. Passive radars are not passive sensors. They measure signals transmitted by other devices, not natural emissions. Another challenge is when sensors are on satellites. They fly over different countries with different radio regulations. As I said, passive sensors are the most vulnerable to RFI. In this image, you can see that both passive and active sensors can experience interference. RFI is shown in red, causing data loss. So those areas have no coverage. Other useful terms related to RFI include out-of-band emissions, or OOB, which are immediately outside the necessary bandwidth, and also spurious emissions, which are non-intentional emissions. Both can be produced by intermodulation products, harmonic emissions, parasitic emissions, and others. And then there's also the definition of harmful interference, which is any emission that endangers the functioning of another service. As I mentioned earlier, in the RF spectrum world, we say service instead of application or use. Here's a partial list of acronyms used for some spectrum services that appear on the FAT, Frequency Allocation Table. For instance, AMS means Aeronautical Model Service, as is the case of airplane communications, and FSS stands for Fixed Satellite Service, which is used for geostationary satellite orbits, or GSO. METSAT means Meteorological Satellite Service. It's used for weather forecasts and for tracking hurricanes, like this image from NOAA satellite of Hurricane Maria over Puerto Rico on September 17, 2017. RNSS is for Radio Navigation Satellite Service, and there lies the Global Navigation Satellites System, or GNSS, which provides accurate position and timing data that is used for GPS. EESS stands for Earth Exploration Satellite Service, and it performs remote sensing of the atmosphere and the Earth's surface with both active and passive sensors, and it also uses spectrum for data downlinks. EESS uses mostly non-GSO polar satellites. They include a large number of applications for scientists, government agencies, and commercial companies. RAS stands for Radio Astronomy Service. It uses mostly passive ground-based observations, but also uses satellites to study objects in space. SRS stands for Space Research Satellite Service. It includes near-Earth and deep space satellites that operate on or around planets or do research in outer space. SRS also includes telemetry and data downlinks for space RAS and other science satellites. There are many more concepts and acronyms, but this is the end of this presentation. If you want to find out more, here's a list of free resources available online that explain some of the concepts of radio frequency spectrum management and the regulation process. For instance, CORF, which stands for the Committee for Radio Frequencies, and it's under the U.S. National Academies, of which I have the honor of being a member for 2 terms, published the Handbook of Frequency Allocations and Spectrum Protection for Scientific Uses, and also published the Spectrum Management for the 21st Century. The National Academies also published in 2015 the Strategy for Active Remote Sensing amid Increased Demand for Radio Spectrum, of which I'm a co-author. Another excellent resource is the NASA Spectrum 101, and of course, the NTIA Manual of Regulations and Procedures for the Federal Radio Frequencies, which is referred to as the Red Book. You are highly encouraged to download these free resources as they will be a great aid as a reference. This is the end of this presentation. I hope that now you have a better understanding about RF spectrum management, the process to update the radio regulations, and that it's now more important than ever to learn more about the fundamentals behind spectrum sharing. Thank you.